In this discussion, we will continue our exploration of complex power and the transformer. We will then introduce briefly the concept of electrical distribution as it applies to residential, light commercial, and industrial consumers. Our first example involves complex power. We're given a source voltage of 480 and an impedance of 2 plus J5, and we're asked to find the power triangle. From your note card, we will need these equations. Voltage is equal to a current by an impedance, and complex power is equal to a voltage by the complex conjugate of the current vector. We know this first one as Ohm's law, and I believe we've called this the power law from time to time. Our opening move is to calculate the current, which is a voltage divided by an impedance. In this case, 480 angle 0 divided by 2 plus J5. That gives us a current of 480 divided by parentheses 2 plus 5J equals, and polar form. So that's 89.1 amps at a phase angle of negative 69.2 degrees. Next, we calculate that complex power. Complex power is equal to the voltage vector by the complex conjugate of the current. The voltage in this case is 480, angle 0, and the complex conjugate of the current is 89.1 at a phase angle of 68.2 degrees. Do be careful. This is a complex conjugate. Our angle on the current was negative, which means we need a positive angle here because the complex conjugate flips everything about the real axis. Using the calculator, 480 times parenthesis 89.1 at a phase angle of 68.2. That gives us a real piece of 15.9 plus, we gotta walk this over a little bit, plus, there we go, 39.7, and that's kVA. We could also put this into polar form. So complex power is equal to 42.8 VA, that's kVA, at a phase angle of 68.2 degrees. The power triangle looks something like this, with 42.8 kVA as the hypotenuse, an angle of 68.2 degrees, 15.8 kW, and 39.7 kVAR. Remember, this is real power, this is reactive power, and this is apparent power. While we have these numbers, there's something I wanted to show you about this problem. And that is, how does it fit in with the rest of the system? For example, I believe last time we talked about a one-line diagram. We'll assume a generator, a circuit breaker, a transformer, such that we have a delta connected to a three-phase Y, And then we'll have some distribution. More circuit breakers. Let there be 3 circuits in this particular problem. We'll send this off to its own load center. And then we'll assume that there are several large motors connected directly up to the system. Generator, circuit breaker, 3-phase transformer. And I suppose you could call this here switchgear. What I'd like to do now is ask you to focus in on this generator and ask yourself, what kind of information could we read from the generator? What kind of information could we build into a generator control system? And I would argue that there are several things you want to measure. One of them is voltage. But not just one voltage measurement. It turns out there are 6 voltage measurements that you might want to make. And because this is a 480 system, that would be 480 line to line. So 480 volts, phase A to B. There would also be 480 volts B to C and 480 volts C to A. But we're not done. We could also read 277 A to neutral. By the way, where did that 277 come from? 277 by root 3 is equal to, there we go, that is equal to 480. So 277 is a line to neutral, 277B to neutral, and 277 from C to neutral. So there are 6 different positions that you might want to measure there. That takes care of the voltage. We should measure current, but not just current in one spot. We want to measure about 89 amps on line A, about 89 amps on line B, 89 amps on line C. We should also measure the neutral current, and ideally we'd have 0 amps in the neutral. Frequency, that should equal 60 hertz. Power, in this case real power, should be 3 times 15.8 kW. You should ask where this 3 came from, and the argument goes something like this. If we have a 3-phase system, we can model the 3 phases as a single phase. So if we assumed that this was for a single phase of a 3-phase system, we could then say that this power triangle actually gets multiplied by 3. So we end up with a very large power triangle. And we have 15.8 times 3, which gives us a real power of 47.4 kW. 42.8 times 3, 128 kVA. The angle will remain the same. And then the bars goes to 119. Once again, we assumed that this represented 1 out of 3 of the phases. We multiplied everything by 3 to get the total power. Let's add some more instrumentation over here. So that was power. We might want to display reactive power. and that was 3 times 39.7 kVA. The last thing we might want to display is power factor. And you recall power factor is the cosine of theta. In our case, theta is 68.2 degrees, giving us a power factor of cosine 68.2, 37.1%. As far as our generator is concerned, you might have a switchboard that looks something like this. These are the meters you might find associated with a generator. Voltage, certainly you would need that. Current, absolutely. The voltage meter would typically be accompanied by a switch. And remember, there were 6 different things we could measure. 1, 2, 3, 4, 5, 6. And that was voltage A to B, voltage B to C, voltage C to A, voltage A to neutral, voltage B to neutral, and voltage C to neutral. With the current meter, that would typically have multiple positions as well, one for each of the line currents plus the neutral. The frequency meter would be simple. And then you have the power meter and the VARs to show what the real and reactive power on the generator is. Anyway, I thought that might be useful when we talk about these power triangles. So you understand that when we talk about real power, there is a physical meter that can tell you what the real power is. Same with reactive power. There's a meter that can tell you exactly what's going on with the generator, or any other part of your system if you like. Let's work another example, this time with a transformer. In this problem, we're looking for the complex power associated with the transmission line that connects the 2 transformers. To calculate the complex power, we're going to need the current that's flowing through the line. We start this problem on the right side where we see the voltage on the secondary of T2 is equal to 480 volts. The current on the secondary of T2 may be calculated as the power, so that's 30 kW divided by 480, which gives us 30,000 divided by 480. That's 62.5 amps. From there, we need to move to this side of the transformer, and all we need is the current. From your note card, the turns ratio is the number of turns in the primary over the number of turns in the secondary, is equal to the current ratio, which is current in the secondary over current in the primary. So in this case, we have 26 is to 3 as 62.5 is to the current in the primary. So the current in the primary, again using some cross multiplication here, is 3 times 62.5 divided by 26, which is 7.21 amps. So the current in the secondary of, the current in the primary of T2 is equal to 7.21 amps. From there, we can calculate the voltage across the line. So the voltage is equal to a current times an impedance. So that's 7.21 multiplied by 10 plus J10. So the voltage on the line is 7.21 times 10 plus 10J. 102 volts at a phase angle of 45 degrees. And finally, we can calculate the complex power lost to the line as the voltage by the complex conjugate of the current. Remember, our power law, S, is a voltage by the complex conjugate of the current. So here our voltage is 102 angle 45, and our current we said was 7.21. So the complex power in the line is 102 at a phase angle of 45 times 7.21, which gives us 520 real watts plus J 520 reactive. We can also put that into polar form if we wish. So 735 VA at a phase angle of 45 degrees. For comparison, remember this is real power. Our line lost 520 watts while we delivered 30 kW. If we had a power flow diagram, it would look something like this. We lost 500 watts while delivering 30,000 watts. Therefore, the input power must be 30,500 watts. What if we were to double this? Let that be 60 kW. How much power will we lose in the line? Will the real power double, or will it do something else? Let's find out. This becomes 60. This becomes 125. This becomes 125 times 3 divided by 26. So that doubles. So that's 14.4. As we keep moving, we see that this voltage moves to 204 volts, angle 45 degrees. It doubles. This here is now 204, angle 45. And our current comes down as 14.4. We can put that into the calculator. So it'd be times 14.4, which gives us 2080 plus J 2080 volt amps. So you can see that's not a doubling anymore. That's actually a quadrupling. And again, if you want this in polar form, we would say this is 2937 VA, phase angle of 45 degrees. If we show the power flow diagram, it looks like this. We have 60 kW, so we doubled our output, but our power lost is now 2080 or 2 kW, which means we had to put in 62 kW to make this system work. The point in all this is to just be careful and be on the lookout for things that do this. Power is equal to I squared R. If you double the current, which we did here, right? When we doubled the power consumed at the load, we doubled the current, which meant we quadrupled the amount of power that was lost to the power line. Moving on, let's talk about electrical distribution. For example, residential. We start with the power lines that are run on the power poles outside your house. We'll call those hot 1. We'll call this one hot 2, hot 3, and finally the neutral. We'll let that extend all the way. If we were to look at the power line itself, it might look something like this. So there's the top of the pole. There would be an insulator here, an insulator here, another one here, and then there would be another wire off to the side here. So this is hot 1, hot 2, and hot 3 with neutral down here. We should recognize that many locations don't have access to all 3 wires. In fact, that's the way my home is. These wires end about a half mile up the road. So all I have on the power lines outside of my house is 1 hot wire and 1 neutral wire. But that works out okay because my transformer that feeds the house is connected up like this. So we have the transformer, this is a fuse, and then the transformer connects to the neutral wire. This is the piece that then goes into my house. For my house, this is mounted on the utility pole. You may have a similar setup, or it's possible you have underground wires, in which case there's going to be a small green transformer somewhere nearby your home. What we're going to do now is focus in on this piece right here. On the primary side of the transformer, you typically find 7200 volts. And know that that is a line to neutral voltage. So if you wanted to know the phase-to-phase voltage running on the power lines outside your house, you could say that volts line to line is equal to √3 voltage line to neutral, which in this case is √3 by 7200. So the voltage line to line is 7200 times the square root of 3. So that would be 12,470. 12,470 volts on the lines outside your house. Inside your home, you would find 120 volts as measured from hot to neutral, and 120 volts as measured from neutral to the other hot. If you wanted to put that into phasor notation, this is 120 degrees at phase angle 0, and this voltage measures 120 degrees at a phase angle of 180 degrees. Another way to look at this is to say that this voltage has a sinusoid that looks like that relative to neutral, while this one has a sinusoid that's 180 degrees out of phase. Know that if you put a meter across both hot lines in your house, you would measure 240 volts. There's another wire in your house known as the safety ground. Inside the breaker panel, you'll find that the safety ground is connected to the neutral. You'll also see a few wires leaving. They go to ground electrodes, typically 2, sometimes more, depending on the code for your area. You may also see a connection from ground to the plumbing of your house. For example, if you have a water pipe entering that's metallic, you'll typically have a connection going to your breaker box to that. You'll notice there's a certain amount of redundancy built into the system, and you'll also find that your building inspectors are really fussy about how these connections are made because they're important. It's called safety ground for a reason. The safety ground plus these connections to the neutral are very important. They keep you safe and they prevent your house from burning down. To better understand residential wiring, it's useful if we look at an outlet. For example, the common one that everybody uses looks something like this. It's a type 515 and it provides 120 volts. This is the hot, this is neutral, and an independent safety ground is also run. Your dryer may have a plug that looks like this, slightly larger lugs. This is a type 14-30, and it provides 240 volts. Safety ground. This is one of the hot connections, and this is the other hot connection. And finally, this is the neutral. These outlets are basically connected where we see the meters, so that 515 would be connected here to give you 120 volts. And you want to balance it out, so you might also have some of them down here. Again, that'll give you 120 volts. The larger 1430 would be connected across both hots to give you 240 volts. If you have an older house, you may find receptacles that look like this. And this is the older 10-30. It provides 240 volts. These particular ones have hot and neutral. You'll notice that they don't have a safety ground. These have been what's called grandfathered into the system. When we say grandfathered, that means it's something that is not exactly safe, but exists in thousands and thousands of homes, so we just leave it alone. New installs would not have this type of connector. They would prefer this one, again, because it has that fourth lug for safety. That was an example of residential. Let's take a look at small commercial. For small commercial, you can expect 3-phase, 5-wire, that's phase A, B, C, a neutral, and then the safety ground. The transformers would be connected up as Y configuration. So here we're connecting each transformer to the neutral, and then we connect this one to A, this one to B, and this one to C. The connections on the primary are made by the utility company. For this example, we'll let this be a 208 system. And I think I told you this. If you see a number by itself, that generally means it's RMS and it's a phase-to-phase voltage, which means that the line voltage, so V line to neutral, is going to be 208 over root 3, which means V line to neutral is 120. So 208 divided by the square root of 3. There it is. There's your 120 volts. Which is kind of a neat trick, because that means you can take a receptacle, for example, that R15 that we introduced earlier, and you can connect it up like this. So there's your hot, here's your neutral, and here's the safety ground. So we'll let this go in this example to phase B. This will go to neutral, and this will go to safety ground. So again, that's your 5-12s, or in a commercial building, you might also see 520s. That allows you to get a little more current out. So this receptacle would be rated at 20, and this one, forgive me, that would have been rated at 15 amps. In this system, we can also have a 3-phase receptacle. It would look like this, with this being the safety ground, the neutral, and then the various phases. We'll let this first one be phase A. We'll let this one be phase B. And finally, this one as phase C. So this allows you to get, oh, by the way, that's an L21-30. That's a 5-wire 208/120 receptacle. Okay, so that was small commercial. Now we can move to industrial and large commercial. These systems can be quite complicated. What I'm going to do is give you a few rules of thumb and then show you a couple definitions that you need to know. So for rules of thumb, We can expect a mixture of high and low voltage. The high voltage will be used for high power loads. It will also be used to run long distances. The low voltage runs will be relatively short. And because of this mixed system, you can expect to find many transformers. As a very simple example, let's assume a factory where this is production and there's an attached office here. The electric feed might come into this panel. Close to that panel, we can expect to find a few transformers. As an example, this one might be 4160 to 480, and this one might be 4160 to that 208. There might be another transformer in a closet over here. That one would be a 4160 to 208. And depending on how many machines are on the factory floor, you could even have a transformer here feeding this equipment, and maybe a transformer here feeding this equipment. Again, many different configurations. It very much depends on the factory's needs. But again, these are some rules of thumb that you can follow. As we move to even larger systems, there are more things to consider. When we use the term large, we could be referring to something like a campus with many buildings. We can also extend these thoughts to the system that feeds your home. So we could talk about neighborhood distribution. Two terms. There are two terms you need to know. One is radial, and the other is loop. When we have large systems, there's going to be something similar to a substation, or at least a central point where all of the energy comes into your campus or your facility. Leaving that substation are wires that lead to individual loads. So on this branch, you have 4 loads, and there might be another branch. And let there be 3 loads on this branch, and maybe this branch here with only 1 user. But you can see the pattern. We have these lines that are radiating out from the substation. The loop takes an entirely different form. It still has a substation. You'll have wires that are, well, they're in loops. But the wire will always come back to the substation. So you might have users like so. The thing to notice is that every user in the loop has 2 paths leading to the substation. For example, this user here could receive power this way, or they could receive it this way. Okay, there are 2 paths. You could argue that there's a little more redundancy with the loop. If, for example, the wire broke, right? Maybe the wire broke right here. And if we assumed that there were circuit breakers along this line, it wouldn't matter because these users would be fed via this path, and these users would all be fed via this path, meaning the system continues to operate even if there's a single wire break. That's different than the radial system. For example, if this wire here broke, all of these users no longer have power. The reason, of course, is that there's no redundancy. For any individual user, there is only one connection to the substation. So if that connection gets severed, any person downstream will lose connectivity. Anywho, that was a brief introduction to the loop and to the radial distribution systems. There's, of course, much more to it, but that's all we have time for today. When you come back, we are going to start our exploration of DC machines.